So from the world of video and audio, we're now going into the world of cloud. So this session is called Cloud-Based Broadcasting and Metadata. And our first presentation, our first team will present a reference architecture for implementing ATSC 3.0 workflows in the cloud, facilitating studio to transmitter link over public internet, and offering a practical framework for researchers and practitioners. We have two presenters for this session. Boris Kauffmann has over 15 years of experience in the audiovisual industry, specializes in broadcasting, focusing on sound and image acquisition. He's a senior specialist solutions architect at AWS, where he applies his experience in systems architecture, video over IP, and cloud-based solutions. He holds a master's degree in electrical engineering and computing, and a Bachelor of Science in Telecommunications Engineering from Mackenzie University in Brazil. Our second presenter, Richard Lhermitte, CTO at Enensys Technologies, where he's developing the company's technical strategy, investigating new technical markets, supporting standardization and patents, and studying new systems and architecture. So Boris and Richard, the floor is yours.
Thank you. Thank you, Pete. Okay, good morning, everyone. So we're going to discuss a little bit of the work we've been doing since last year about virtualizing a full ATSC3 stack, and also investigating a little bit how the dual delivery of broadband and broadcast being delivered from the cloud into the same reception could be leveraged for failover mechanisms for the RF delivery. So the motivations are because ATSC3 is already published. It's implemented in 4 countries already. It's rolling out in the US, and recently Brazil adopted core technologies of ATSC3 for our next-gen television standard. There are, of course, solutions in the market already. All of them are soft-based, so they technically could be run in the public cloud, except from the modulator and the amplifiers and antennas. Everything can be virtualized and run from the cloud. And also to understand a little bit the technology implications, because this change is already happening in the play outside. So we've built and implemented a fully working system, ATSC system, and in order to evaluate those challenges, we also opened the possibility to leverage the same resources to deliver broadband and broadcast. On more specific objectives, study how the STL, the Studio to Transmitter Link Transport Protocol from ATSC, could be delivered from the public cloud to the ground. For doing that, we had to validate if the ARQ protocols like SRT, RIST, or 6C could be the solution to protect that stream, very critical stream, could not lose any packages. And this also allows us to do tests regarding how the CDN and the STLTP could be delivered from the cloud in a synchronous and seamless way. So this was the reference architecture we implemented. From the left, you can see the live video coming into the playout system, which is already virtualized. The program output of the playout system, it's a transport stream, is already feeding the dash encoder in your traditional linear over-the-top delivery. So this dash encoder is already delivering to an origin, and this origin over the CDN delivered to your viewers, traditional broadband delivery. So why not bring also the broadcast stack up to the cloud to optimize, resources? So the same dash encoder that is creating the manifests and segments are being used to feed the route server that is going to take those segments, create the route sessions, add a lot of tables that are required for ATSC3, add the electronic service guide, add the data casting, non-real-time assets, and then over multicast deliver that to the gateway. The ATSC3 gateway will add the tables, modulation parameters, all the bootstrapping required for the modulator, and then we bring the STLTP down using fiber, but in our case, public internet down to the exciter, modulator, and then antenna. So the viewer has the option to receive that over the air or over the top.
Yeah, hi everybody. Boris already explained, ATSC3 decided to change a little bit how they deliver the video. Initially, on a traditional broadcast system, we rely on transport stream, that's a traditional transport packet, and we deliver it on a one-way to many end user. What has been decided by ATSC3 is to use the packetized way we are doing on broadband access, meaning that we are not delivering a flow of packet, but we are delivering files. So we will rely on the dash mechanisms to put some segment or some chunk that will be delivered over the broadcast. So we are no more in, let's say, RTP, UDP, transport stream over IP delivery, but file delivery for ATSC3. To do a file delivery over broadcast, ATSC3 decided to use one specific protocol, which is called root, which is over there. So if you want to deliver a file over broadcast, you use root, and the same file over broadband will use the traditional HTTP protocol. So it means that, as Boris explained, one dash segment that has been published by the encoding stuff or the packaging stuff can be delivered over broadcast using root and over broadband using traditional HTTP. That's important to understand that there is no more transport packet now in ATSC 3.0. In top of this multicast stream that have generated over root, because root is multicast delivery, you have one root session per service. You need to have some classical signaling. The signaling is the way for the receiver to understand which services are available on your network and how they are composed. So you have classically two main tables in the ATSC3 protocol. One is called SLT, which is the list of the services you have on your RF channel. That look like a PAT table for transport stream. It gives you the list of services. And this SLT is delivered over a defined and reserved IP multicast stream. That's a fixed IP multicast that the receiver has to receive first, like the PID0 in a transport stream. So the SLT is the entry point, and then it gives a link to all the different SLS, one SLS per service, which provide the architecture of each program. How many video stream, how many audio track, is there any closed caption, and so on. So the SLS provides such kind of, let's say, advanced information about the service. And all of these services must be delivered, as Boris said, from let's say the broadcast station to the transmitter site. And to do that, ATSC has decided to make a tunneling, so all the multicast root session will go over one unique multicast stream, which is called STLTP, Studio to Transmitter Link Transport Protocol. That is one multicast stream from studio to transmitter. And it's a really tunnel because it contains all the different services, all the different root sessions for the different services, plus additional information for the transmitter side, typically the synchronization part. There is a SFN in ATSC3 for single frequency network. So you need to have a precise timing information that is provided by the STLTP and all the modulation parameter that the transmitter has to also deliver. So this is one tunnel, one multicast stream, which is very important because it contains all the content that has to be over the air. And this is this STLTP that will go from the cloud to the transmitter side. And this is this STLTP that has to be delivered in a very reliable method to ensure that no packet are missing from let's say the encoding, multiplexing, which is in the cloud, and the transmitter side.
So how this is a very critical stream, and it's a generic UDP stream. It's not an MPEG-TS. We investigated which ARQ protocols would allow this transport. And of course, SRT and RIST was the obvious choice because they support taking that multicast UDP, converting to unicast, deliver that to the public internet, and reconstruct that multicast on the exciter side. So for those who are not familiar with ARQ protocols, basically the sender keeps a buffer of the delivered packages while the receiver is getting those packages. And if, let's say, package 2, 5, and 6, for example, weren't delivered or arrived out of order, so the receiver has time, because there is a buffer, to request over non-acknowledged messages back to the sender and say, hey, look, I didn't got 2, 5, and 6, please send me back. Then the transmitter will send it back, 6, 5, and 2, retransmitted, and then the receiver is able to really put all those packages in order and deliver to the exciter. So that way we don't have any type of interruption in the RF stages. So just to recap, this is the order that we implemented the whole thing on the broadcast delivery. So we use Titan Live encoder because it's already provides some templates on service configuration, supporting all the ATSC3 codec audio video standards. We deliver those dash segments to the route server, NNC's MediaCast in that case, adding all the tables required, creating the LLS. This becomes route sessions over multicast, which are then delivered to the ATSC3 gateway, which is in that case SmartGate from NNC's, adding all the modulation parameters, creating the PLPs, and then delivering the STLTP over multicast to a tool. We basically compile the librist and the libsrt from the public GitHub repositories. Like, we created the interface just to give some idea of the transport health. And then on the on-premises lab, our labs, we reconstructed back the STLTP and feed the modulator analyzer. So that screen shows on the left the actual STLTP over IP being decoded by this transport analyzer. And on the right, you see the actual output of the modulator, the RF signal that was demodulated and presented. So you can see that it actually works. This is a picture of my laboratory. Those are the modulation parameters used in that test. So around 32 megabits per second streams. This is Richard laboratory with the NNC's modulator there, same test. And we run a bunch of different tests, different configurations on ARQ, and we're going to present some time series, some plots about it. But the idea is that all these hack of equipments were converted to only 4 EC2 instances in the cloud, and a little bit more optimized in terms of compute. You could apply the right compute quantity for the actual work that needs to be done, instead of having like a big server just to run sometimes a simple signaling software. So we brought just 2 plots here. So the first test was let's say the most complex one. We instantiated this whole system at Oregon AWS region, US West 2, and we deliver over public internet back to NNC's laboratory in Reims, France. So it was like a 5,000 miles distance, 162 milliseconds round trip time. And so we configured the buffer to around 4 times this, so around 700 milliseconds. And you can see from the plots, the first plot shows the round trip times, the round trip times calculated by the receiver. You can see some jumps, some changes that happens in an unmanaged public network. The second plot shows the packages that were not received by the first time on the SRT receiver. And the third plot shows the retransmitted packages. And this means that all the lost packages were retransmitted, were received. And the fourth plot, you see no dropped packages. So we could reconstruct 100% of the packages on premises using a fine-tuned combination between ARQ and FAC on the SRT lib. And this runs for 8 days. So we left this running really, really long time to see if it really would work in a real-world situation. The other test was a little bit easier from a compute perspective and round-trip time perspective. It was São Paulo region in Brazil and my laboratory in Itatiba. It's just 8 milliseconds, 44 miles from the actual data center. So I could reduce the buffer a little bit, but there still could be reduced a little bit more. But I chose to work with 200 milliseconds. Same results. SRT, you can see a little bit better RTT profile on the first plot. Again, lost packages, retransmitted packages, and no drop packages using the SRT lib. Same thing with RIST, same good performance, so same idea. All the missing packages were recovered, no lost packages at all, and we were able to cross-reference that with the modulator logs. No problems were found on that side.
So even if we are using such kind of failover protocol, what happens if one STLTP packet is missing? It's important to understand that on the modulator side, missing one packet will be like a disaster, because the modulator will break its synchronization with the gateway which is sending the STLTP, especially regarding what I said previously, the SFN part, which is a timing information to deliver the content over the air. So the modulator will stop and restart the synchronization, even if only one packet of STLTP is missing. Right after the modulation, you have the amplifier stage of your transmitter. According to the power of your amplifier, it will take from 1 second, 2, 3, 4, 5 seconds to restart all the amplifier stage, because an amplifier and transmitter will not start immediately all the amplifier stage. So you have between 3 and 5 seconds, depending on the power of your transmitter, restarting of the transmitter. And then on the receiver side, the TV set at home or the set-top box will desynchronize and resynchronize due to this stop and restart of the RF signal. It will take, let's say, 1 second on the receiver side. So that means that one missing packet on the SCLTP delivery is around 5 seconds of blackout of your RF channel. So all the services which are inside this RF channel will be blackout during these 5 seconds, which is very important in terms of, let's say, quality of delivery. So one thing we were thinking about is, due to the fact that we have this broadband capability of delivering the same content thanks to ATSC3, will it be possible to use this broadband, let's say, link to get the same signal and the same content for the services? So that could be possible. So the first point we need to be to ensure is that this service, this content is available on broadcast and broadband simultaneously. So what explained Boris is that the same content should be delivered over these two different networks, exactly the same dash segment, etc. We need also to ensure that on the ATSC3 signaling level, the receiver knows that if there is no more access of the content over broadcast, how to do to get the content over broadband. There is some already signaling information in ATSC3, but nobody already made this test in real life. There are some tricky information that you need to insert at different level of the signaling in the SLT and the SLS. This is what we propose to do, is to make this signaling information to allow the receiver to get the service first on the broadcast, and if there is a failing of reception, fall back to the broadband. And of course, if the broadcast is restarting, go back to the broadcast, to have the broadcast as the main reception for the receiver. And we need also to ensure that the receiver has this capability. It's not easy for a receiver to decide when there is a failing of reception in one way, how to switch and seamlessly to have no glitch on the video and to have this seamless switch to broadband and vice versa. So it's not only a description of the capability on the signaling level, it has also to be implemented on the receiver side. So if we succeed to have such kind of, let's say, automatic switch between broadcast and broadband, what are the advantages? Of course, it has this possibility to make this failover capability if the RF signal is failing. That's another possibility if you have just during a temporary situation where the RF is not received in a car, for example, you can switch to broadband. But that's also an opportunity for broadcaster to dynamically decide which content can be put on broadcast and which content can be put on broadband. Typically, if there is a specific event on a channel and the broadcaster decide to put it on broadcast because a lot of people will watch it, you can imagine that dynamically the broadcaster will put this service on broadcast. And at the opposite, he can also decide one service to be less popular for a period of time to go back to broadband only. And on the receiver side, and the end user will not see the difference. He doesn't know where the service comes from. Or there is another idea. If you have a 4K event on a specific channel and you want to deliver it, you don't have enough space on your broadcast over the air system because you have other channel. You will switch temporarily this additional channel to broadband to keep the broadcast 4K service on air during this event. And then you will fall back to broadcast when it will be done. So that offers also a lot of flexibility of the broadcaster in terms of allocation of these over-the-air RF channel. But come back to our situation. If we have this SCLTP failure during, let's say, one packet, as I explained previously, it's probably 5 seconds of blackout. So if all the receiver has to fall down to the broadband access to get this content during this 5 seconds, because that's what we expect, what could be the consequences? So we took, and I will let Boris explain for the CDN part, but we took an example which is really the worst case. It's Sao Paulo. Sao Paulo, you have around a bit less than 7 million of people watching TV over the air. And imagine that all these 7 million people are watching the same content at the same time, and unfortunately, you have this 5 seconds of break of RF channel. So all this will have to switch automatically to the broadband access, and that is where this computation comes from.
Yeah, this is, if you see the calculations, a 5 megabits per second service would be being tuned at the same time by almost 7 million devices, which is the situation at the São Paulo metropolitan area, would gives us approximately 21 terabytes of data. And those 56 terabytes needs to be served by the CDN in a very short window, like a 5-second window. And this translates in terabits per second into about 35 terabits per second, which it's not, for a big CDN is not a problem, but the thing is we are working with the overhead of the baseline. The CDN is there serving, but you will require for a short period of time an overhead of 34.5 terabits per second, which in some regions is not available, is not a reality. So as you can see, the power of the RF in terms of data delivery, it's much capable than the CDN. So what would be the strategy? So normally the CDNs, in our case, CloudFront, does have a hierarchical caching approach. So those requests are not hitting the origin. They are actually hitting the CDN. But when we call CDN, we are talking about a combination of levels. So you have the edge locations that are closer to the viewer, very spread out. Then those edge locations will actually try to get the content from the regional edge caches, which are bigger POPs with bigger storage capacity. And then those regional caches will go up to the origin. So there is also a mechanism that as soon as the first request comes and the first byte is served for the first viewer, while the file is flying to the cache, it already can be served. It doesn't need to stop to complete the first segment to be downloaded to the edge location. It can be served while it's copying. But even though a multi-CDN approach will be required in that case, because you need to combine the capacity of multiple CDNs in order to provide, it will not be just the CDN, the actual network, the ISP network, the BGPs, all the actual underlying internet providers need to catch up with that burst. So it's a challenge. It's something to study and verify how this could work. But in terms of considerations, we documented this whole deployment. We shared with manufacturers the findings for future product enhancements. We validated the use of multicast between those components in the cloud, which multicast in the cloud is not normally allowed because of scaling and security reasons. You have to explicitly say that you're going to use multicast and configure a network that way. We validated that ARQ protocols are feasible solution to transport the SCLTP without errors. And this handoff between broadcast and broadband is somewhat defined in the standard, but more testing and implementations are required to actually validate that this would open those opportunities, including target advertising if you would like to switch to broadband during the commercial break for some specific regions, let's say, using DNS mechanism. So that was the closing thoughts. Thank you very much. We could take some questions. Here is our contact. Thank you very much.
Thank you.
So the missing packet's quite a problem if it goes missing. But you've got the receiver checking whether it missed a packet and requesting it. If that request packet gets lost, then it will never get the resend. Why not have the receiver acknowledge every packet that comes in and have the transmitter realize a packet was not acknowledged and then proactively resend that one?
So in reality, the receiver will receiving from the air a manifest and files. And inside that manifest, there are files that are hosted locally on the setup box. And on that manifest, there's also a URL that is pointing to the CDN. So actually, it's not the transmitter that is resending, it's actually the receiver will need to look at the manifest. When he doesn't find the file that didn't arrive because of the RF problem, he will need to go to that URL, ask the CDN for that segment, and then put that segment in let's say, in the queue, and then play it out. So the complication on the implementation, if you want to complete.
Yeah, the complexity is how to declare that the service is both available on broadcast and broadband. In ATSC 3, they define how to deliver over broadcast. They define how to make signalization of a broadband service. They call it a virtual channel, but they did not really finalize the way to declare how the service is available on both broadcast and broadband and which one is a priority.
And of course, we require inside the set-top box a little bit of buffering in order to have time to make this HTTP request and add the missing segment in the sequence. So it's more on a receiver and implementation challenge, I think.
Good morning, John Furter, Quest US. Thank you very much for your presentation. I was wondering from a practical standpoint, I was very interested when you were describing your failover scenario. And my question is, have you simulated a failover? If so, how many times did you do it? And how consistent were your results, especially compared against your computations?
I didn't get the last part.
Yeah, I heard the first part, which did we have simulated the failover? Unfortunately not. We have the failover, we have simulated the failover because we are able to, at the transmitter side, to lose some packet if we want. But we were not able to simulate the capacity of the receiver side to go to broadband to get the missing packet or the missing dash segment. So that's what I just explained. It's potentially described in ATSC 3, but as for today, as I know, there is no receiver able to make this seamless switch. That's something for me that could be interesting to study and to propose to ATSC 3. It's to make additional, let's say, plug phase to understand if it's a solution that could be interesting for the broadcaster and how the receiver should make these failover mechanisms in case of missing or bad RF transmission. But yes, we did not succeed to have a receiver which is able to make this broadcast to broadband access.
Over here.
Hi, Steve.
Hey, Richard. So, in implementing what you're describing, is there any necessity to make any changes at all in the STLTP? My understanding from your presentation was that there is not. So then a follow-on question to that is there any implication when a station operates with a single frequency network and transmitters are transmitting at different times in order to do network shaping? Does that have any impact on what the CDN has to do in order to make up for the missing data?
I will answer the first part regarding the STLTP. So for me, no, there is nothing to change on the STLTP. Everything which is defined on the STLTP is good enough. There is nothing to change. We had a question when we started the test is there is the FEC capability on the STLTP, and there is also STLTP on the SRT level. So what is the best? Is it to use the STLTP on the forward error correction on the STLTP, or to use the forward error correction on the transport SRT level? Finally, we decided to use only the FEC on the SRT level because SRT is managing the transport itself, so we were considering that it's better to put the FEC at the transport level than at the data level. But that's something we can try on the second phase, is to mix also FEC on both levels. So no, there is nothing to change on the STLTP. What I understand, what I have to be validated for me is mostly the signaling of the services availability on both network, but nothing to do on the STLTP. But Skip, I did not understood the second question. Sorry, can you repeat?
If the broadcaster is using a single frequency network and that adjusts the time of the transmitters, emission times of the individual transmitters in order to do network shaping, does that cause any need for change in the repair delivery through the CDN, or any additional complexities in the repair delivery through the CDN?
I don't think so, because the SFN will be, let's say, will not be broken by the fact that one transmitter will continue to deliver the STLTP and the signal on air. The second one will stop and restart. So during this period of time, this one will continue to broadcast, and when this second one will restart, then the coverage will be increased, but the SFN will not be broken, because this is the same STLTP which is delivered to both to synchronize for the SFN. So for me, there will be no issue.
Well, it would depend on whether or not a particular receiver is receiving from multiple transmitters or a single transmitter. But the transmitters could very well be emitting at different times, offset from the bootstrap reference emission time. And so the question is, does that have any impact on the delivery of the repair packets through, or repair files through the CDN?
I'm not sure I'm able to answer that. Probably we need to have a deeper.
It might be something worth thinking about.
To investigate. Thank you. Okay.
Thank you very much, gentlemen. Very great and interesting session.